Section 7.4 concerns work by a varying force. All right, we're going to build up to it, but I think it's going to be no surprise how we do this. So if we consider some path, then object moves along, and we consider a force acting on it as it moves along that path. Say this is a hill that we're pushing along, and we're going to always push with a horizontal force. So and here I've set up where I have a varying path and a constant force, right? But we could have a force that varies too. So let's look at something like that. Let's say that we have a pulley and a box being dragged across the floor over the pulley, right? By pulling down here. So as the box moves across the floor, the angle of the rope is going to change, and we could change the magnitude of the force as well. So here you see we've got the box being pulled at this angle. And as we get closer and closer, the angle changes, right? And we can vary the magnitude as well. So there's a varying force, and here's a varying path. Here we've got a nice straight line path. But if we look at either of these, the thing that's changing, besides the magnitude of the force, which we can vary the angle as well, either aspect of the force. So what you do is you break it down into small segments. And we consider, over this small delta x, let's just use the second one here. Over this small delta x, we've got this average force. Between two times over here, we've got a small delta x. And we've got this average force. And what do? We sum up the work done well, let's use an index here and then n for the last one. Right. The work done over this for however many segments we break it up into. In this case, we've said n segments. So we would do a sum of the work over all n segments. And we would find that by the average force on that segment times the displacement for that segment. And here I'm assuming all the segments are the same length. And times cosine theta on that segment, right? And we talked about this. This is that f dot x. Let's use the vector notation here since we're writing it in a dot notation. All right. Well, I lost my summation. All right. What do we do whenever we have a summation that we want to make more precise? This is how you learn calculus, right? You start with a Riemann sum and you work up to making that an integral, right? If I have some graph, I break it into segments and I calculate an approximate area under each of those segments. And I add up each of those segments, right? This is what we're talking about here. This would be my delta X, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N would be 11 for my example here. And we would add all of these up. And you can see that if you increase N, then you get a more accurate sum. And that's what you do when you do calculus, right? As we let N go to infinity, our summation becomes an integral. So when we're talking about the work done by a varying force, we're going to use an integral. So work then is going to be the integral of f dot dr. I know I've been switching between x and r, but f dot dr between, some point A and some point B. What more do I want to say about that there? Let's do an example. Right, we've talked about springs and we talked about how you look at the spring force at a given stretch, right? We know that the spring force is minus K delta X, where X is the displacement from equilibrium and K is the spring constant. And that means if I stretch a spring over some distance and I want to know how much work is done stretching a spring, I have a varying force. So let's look at this first if we stretch it starting from the equilibrium position. So first, let's start in equilibrium. So I've got my spring and our x naught is our equilibrium position. And we're just going to define that to be our 0 for our x. And then we're going to stretch the spring out some distance, delta x, from the equilibrium position. And we want to say how much work is done stretching the spring. Right? We know work is done because in order to stretch the spring, I have to apply some force. And that force acts over a distance because we move a distance. But that's not a constant force. Since F depends on delta X, it is not a constant magnitude. Right, in this case, we're going to have delta X and F acting in the same direction, so that's not a problem. Just the fact that the magnitude is changing. So if we look at our integral, work is the integral of F dot dr. Well, the whole time even though f is varying in magnitude, it's acting in the same way that we're stretching. So cosine theta is equal to 1 because the angle's 0. So we can actually get rid of the dot product right here and just say that we have the integral of f dr. What does f look like? Well, f, we said, was minus k delta x, where x is your displacement. What does dr look like? Dr in this case is just dx because it's one-dimensional. So our work then is equal to the integral minus k delta x. Well, this is the spring force, and we're actually talking about the force acting on the system. So let's draw a free body diagram and work that out. So we know that the spring force is minus k delta x. So if I'm stretching the spring to the right with some applied force, which way is the spring force? We know that the spring force then is going to be back to the left, right? So actually, I don't need the minus sign here is my point, right? So what we have is k delta x, well, just x, because we defined our starting point x naught as 0. So then if we have delta x equal to x minus x naught, that's just x, right? That's why we chose that coordinate system. So now I've got 1/2 kx, and I'm replacing dr with dx because it's one-dimensional. All right, and k is a constant. I can bring that out of my integral, and I've got x dx. And we're stretching from our initial point, which we said was our 0 point, to some value x final. What's the integral of x dx? Well, that's 1/2 x squared. And we're evaluating it from 0 to x final. And we've still got our k out front. Right, everybody may not be that comfortable with integrals yet. You're probably in Cal 2 right now. And you probably only touched on it just a little bit at the end of Cal 1 as an antiderivative, right? So if we look at x squared and we take a derivative, we get 2x dx. So if we look at we can divide each of these by 2, and we would have 1/2 x squared and x dx. So now if we look at the integral of x dx, we can see that it's 1/2 x squared, right? So thinking of it as an antiderivative here is okay. I'm sorry, my weather radio's doing its monthly test. Let me pause. All right, I'm back. A little tornado warning there, just a test.